Let's provide an overview of the most important type classes in Haskell. So we had already seen the EQ class. That's a good starting point. So let me start GHCI again without loading any file and just look at the predefined equality class. We always have to scroll up rather far because of the many tuple instances. Right? At the context of the EQ class, we had already seen that classes can have multiple methods. Methods don't have to be operators, of course. They can be symbolic operators, but they can also be alphanumeric names. And they can have default definitions. The default definitions themselves are not shown in this view, but what is shown is this minimal pragma that we have seen that can be used to give an intuition to the programmer that when we define an instance of a particular class, what are we expected to actually provide definitions for? Because in the presence of default definitions, this is important, right? In this particular case, we have a choice whether we want to implement the equals method or whether we want to implement the not equals method. The one that we are omitting is automatically getting its definition by means of the default. Another class that is very important is the Ord class. The Ord class provides ordering, right, and comparison operators. So again, we get a lot of output for lots of instances because for the largest part, the instances of the Ord class are quite comparable to that of the EQ class. We see that the Ord class has many more methods than the EQ class. It has compare as a method. It has less than equals, greater than or equals, and the maximum and the minimum functions, the binary maximum and the minimum functions. And it also has quite a number of default methods, apparently, because the minimal pragma says that we have a choice of implementing just like we basically need to give just the definition of a single function, and we can choose whether that single function is compare or less than or equals. Now, what is this compare function? That's perhaps the most mysterious one because it mentions this ordering data type. So again, we know our :i command, so we can just ask GHCI, what is ordering? And we see that ordering is a simple Haskell enumeration type. It's a data type that has three constructors. The first one is called LT, the second one is called EQ, and the third one is called GT. And none of these constructors have any arguments. And they just stand for less than, equal, or greater than. And all that compare does is it compares two values and gives us in one go a specific result between these three options. It tells us whether the first argument is strictly less than the second, then it returns LT. Whether the two arguments are equal, then it returns EQ, or whether the first argument is strictly greater. So if we use the already existing instances of the Ord class to call compare on two integers, for example, on 3 and 5, we get LT. If we call it on 4 and 4, we get EQ. And if we call it on 10 and 1, we get GT. So that is the compare method. And if we define our own Ord instance, then defining this compare method is one of the options that we have. The other option that we have is to define the less than or equals method. Now you could ask yourself, isn't less than or equals too weak? I mean, because if we only have less than or equals, then how can we derive from that the notion of when the two values are actually equal? But if you go back to the output for the Ord class, we see that there is one additional thing which is new, namely that we have such a constraint here, which is on the class declaration. We have seen constraints, extra constraints on instance declarations before. Up here, when I defined my own instance for lists. I said I can only define an instance for list of A's if I already have an instance for EQ on A. Here this is a little bit similar. It says that EQ of A is a so-called superclass of Ord, and it means that I can only make something an instance of the Ord class if it is already an instance of the EQ class. So that means that if I make something an instance of the Ord class and define less than or equal, then in particular there must already be an instance of the EQ class that defines equals. And if we have both less than or equals and equals defined, then we can derive from that the notion of when something is strictly smaller, right, by saying it must be less than or equals and not equal. So that is the idea here. So we learn of a new feature here that is this notion of superclass constraints. And we can actually try to play with this ourselves in our own mirroring. If I'm also hiding the Ord class for the time being, and I'm trying to give my own implementation of the Ord class here, where I'm going to give fewer implementations of methods. So let's perhaps just add this less than or equals operator and nothing else. Let's say that's the only method that we have in our Ord class. And now I'm going to give an instance of the Ord class for booleans, let's say. And I want to say when is a boolean smaller than another. And you'll see that there is an instance of Ord for bool defined, but I mean the question is actually which one is smaller than the other, and there are good cases to be made in the case of booleans for both, but the general idea here is that false is considered smaller by definition than true, and we are going to re-implement this. So we have multiple choices here, right? If we want to stay somewhat systematic and say x is less than or equal to something, let's in this case let's just do pattern matching on the first argument, and let's consider that we have false less than or equal to y, or we have true less than or equal to y, right? And we are going to say that for false being less than or equal to y, because false is the smaller of the two booleans, this is always considered true. Okay, and for true to be less than or equal to y has to be true. I mean, true is the larger of the true booleans, and so only true is larger than true. So y is greater than or equal to true exactly if y is true. So we can just return y here. Okay. If I now load overloading.hs back into GHCI, so I'm leaving the prelude context, but I'm in the context of my Ord class, right? We can now see that with our definition of false, of less than, we can compare false less than true, and we can compare true less than or equal to true. We don't have the other methods available at the moment. So if we wanted to add something like this less than, we would actually have to do it ourselves. So we would have to add to the class, have to add this method as well, and give it a default definition that says x is less than y. Is exactly the case if we have x is less than or equal to y and not x equals y. And we can use equals here now even in the default definition because EQ is a superclass. Right, so that is allowed to us. And then if I reload and ask whether true is strictly smaller than true, then I get false, whereas it is still less than or equal to true. If I if I start making my own instance for Ord for another type, so for my own Ord class, if I, for example, try to say something, I can define an instance for maybe A. If I have an Ord instance for A, then I'll get an error message, not a warning in this case. And actually, there is a little bit of a strange output here. I think this is a side effect from Haskell language server leaking some implementation details. So this is actually not very nice, I see. But the important error message here is the one that we get, unfortunately, at the very end. That says, could not deduce EQ of maybe A arising from the superclasses of an instance declaration from the context Ord A. So we get an error message when we're trying to make maybe A an instance of the Ord class, because we haven't made maybe A an instance of our own EQ class. So we have to do this first. Right? We have to do first an instance of EQ A, EQ maybe A, and then of course give the definition of equality as well, but now you can see that everything has been turning back into warnings. So now if we actually provide the definitions of equality and ordering, then this is going to be okay. All right, so that is the Ord class. And we can see, if we look once more in the normal GHCI, in the prelude context, we can see once more that there are actually quite a few instances for Ord. And in particular, perhaps surprisingly, there are also instances such as an Ord instance for lists, and there is also an Ord instance for tuples, for pairs. Right? So actually quite a few types have an Ord instance. And you can ask yourself, what is the ordering of a list or the ordering of a pair? And basically, whenever there are multiple things to compare next to each other, then the default ordering that Haskell uses is lexicographical ordering. And we can observe this nicely if we try to compare lists of integers according to the standard ordering. And so first of all, smaller lists are always considered, like shorter lists are always considered smaller than longer lists. So the occurrence of the nil constructor is considered to be smaller than the occurrence of the const constructor. If we try to compare the empty list with the list containing, or let's say just 0, we'll see that it is considered to be strictly smaller. Now, if we have two lists that start with 0, right, then the rest of the elements matter. So again, if one of the lists is longer, then that one is considered greater as well. Right? But if they both have the same length, then we actually start comparing the elements, and it matters that 0 in the second position is smaller than 1. And if we make the second element larger, then 0, 2 is now considered larger than 0, 1. Right? Whereas the first element still dominates, so even if we have 0, 2 and we compare it with 1, 1, now the first position is already different, and 1 is greater than 0, so then it is already considered greater. So this is what's called lexicographic ordering, right? So also means that for strings, which are lists of characters, we get more or less the standard ordering. If we compare strings that have a common prefix, then the first character where there are different matters for comparing the strings. And for pairs, we have essentially the same situation. Let's move on to other type classes, and let's have a look at another type class that exists that is called enum. So the enum class is another class that you are sometimes going to be confronted with. And so it again has quite a few different methods, and the most important methods, I guess, are the enum from to and enum from and perhaps enum from then methods that we've already mentioned, because they're essentially what the list range notation is getting expanded to if you use it, and that is the main contact point with the enum class. So we have been using 1.10 quite a number of times, and we have been discussing that it's essentially the same as saying enum from to 110, but really enum from to does not just work for integers, it also works, for example, for characters. And then we get a string between these ranges. And in fact, it works for everything that is in the enum class. So if we write our own lambda term that says, let's take a lower bound and an upper bound and compute the ranged list from x to y, then you'll see that you get this enum constraint here. Now that is coming because this translates into an enum from to call, and the enum from to call has exactly this type, that it takes two elements out of A and turns them into a list of A. Right? This is exactly the type of the enum from to function. So now with this knowledge in mind, let's have another look at the enum class. So what does it have? It has a successor function that for a given element provides the next element. I have to attach a little bit of a warning sign here, because the successor function is in general partial, so it can crash. So you should really use it with caution depending on which type you're at. For integers, it's fine. There is always a successor. For integers, there's also always a predecessor. But there are also bounded types that are an instance of the enum class. So for example, bool is an instance of the enum class, and you are allowed to write something like go from false to true, and you get false true, again in line with false being considered smaller than true, because if you go from true to false, you get the empty list instead. Right? Similarly, for how you couldn't go from 5 to 0, it would also give you the empty list. But whereas you can take the successor of 5 to get 6, and you can take the successor of false to get true, if you take the successor of true, you get a crash. And similarly, if you take the predecessor of false. So successor and predecessor are an instance of the enum class, but they are partial, so you have to use them with caution. At least in general, they're partial if they're used on finite or bounded types. Similarly, to enum and from enum are sometimes useful, but also a little bit dangerous. So they allow you to convert between integers and the values of appropriate type. And the integer mapping is supposed to be consistent with the enumeration behavior, right? So essentially, if you can even see this mapping to integers as the way that indicates the ordering of the enum class. So, for example, if we do from enum false, we get 0, and if we do from enum true, we get 1. So that also indicates that 0 is considered smaller than true, or the predecessor of true in the context of the enum class. If you want to define your own instances of the enum class, then again, you don't have to give very many of these options. You have to provide both the to enum and the from enum methods. So this is a comma, not a bar. So this actually says you have to provide both of these. So essentially, you just have to say how the enum type maps into the integers, and then the ordering on the integers is taken as the indication of how the enumeration actually works. And we see in terms of the predefined instances, there are far fewer instances of the enum class than of the equality and ordering class that we have seen before. But we have our usual suspects. We have an instance for int, we have an instance for bool, we have an instance for double, which is a bit strange. I'll say something about this, and we have an instance for character in particular. So the instance for double is actually a little bit strange and perhaps should not really be there, because in in my mind, enumeration is always like enumerating all the values, and for doubles this is done so that you can use this list range notation on doubles as well, but it takes the somewhat arbitrary choice of also just providing essentially integer steps. So if you do 1.0 to 4.5, you get even the strange behavior that you get everything up to 5.0. So you have to be really careful here, that if you provide some sort of strange fractional boundary, you may get an element of the list that is past that upper bound. So this is a really strange behavior. And you always get like 1.0 increments. So you can also start from 1.5 and go up to 4.5. And now you see that actually it's stopping at 4.2. So it's not even always going past this. This has something to do with rounding. So I think I would be very careful here. I would basically just stay away from this enum class behavior when it comes to doubles and choose other methods of being precise about what you mean rather than relying on this. But this instance exists. It is useful to briefly talk about the other enum from methods, because they also have their associated syntactic sugar. We have been seeing enum from before. Enum from is what is being used if you omit the upper bound in a list. So you get essentially an infinite list that starts at the given number, or a possibly infinite list. If you do this for a type that does not have infinitely many elements, you still get a finite list, right? But you just get all of the elements up to the end, and then it's done. And then you have enum from then to, right? So we have, this is too long. Let me just repeat the Ord class the enum class once more. Then we have enum from then and enum from then to. So they both allow us to give a step width next to a possible upper bound or omitted upper bound. And they also have other notation. So we can do something like 1, 3 up to 10. So that tells us we want to start with 1, but then always omit one element, and then step in a step width of 2 up to the upper bound. And then we stop at 9 here. Or we can choose a step width of 4 or even of 5. Right? Of 3 or 4, not of 4 or 5. So here we have a step width of 3, always incrementing by 3. Here we have 1 by 4. And again, we can also actually omit the upper bound. Then we get the step width, and we can see that there's always an increment of 4, even for the larger numbers that we're getting, but we're just going on forever. That's the enum class. And then one more class that I want to look at is the bounded class. Bounded class is rarely really important, but it is one of the basic classes, and in few cases it may be useful. The bounded class has just 2 methods, and they're both constants of type A, and they're essentially saying that we can get the smallest and the largest representable value of a data type out. And the minimal instance in this case has to define them both, so there are no default methods involved of default definitions involved of any kind. And we do, for example, have an instance for bool, which is not so surprising now, I guess, because the what is the smallest boolean. So here, one thing to keep in mind is if we actually just type min bound, it is not so clear what type do we actually mean. There's no contextual information now. The type of min bound is bounded A, double arrow A, but we have we don't provide any further information. So which instance is it going to choose? What is it going to tell me the smallest value of booleans? Is it going to tell me the smallest value of integers or the smallest value of characters? So what choice does it make? All right. Or does it make a choice? In fact, it could just give an error message, and we'll see that in principle there are two options here, and both of them are taken by GHC from time to time. One is to complain about not having enough contextual information to resolve the overloading, to complain about ambiguity, and the other is to just make a choice, to make a choice according to certain rules. In this case, GHCI is going to make such a choice. And this making a choice in such an overloaded context is called defaulting. Defaulting we have actually not mentioned before, but we have seen it happening implicitly behind the scenes a couple of times, primarily in interactions with GHCI. And in this case, it will default to the unit type. So in many cases, GHCI, when there is any defaulting to do, it will just choose the unit type, which is often a useless choice. Right, but it is a type that has very many instances, actually. So very often, at least some result can be provided. Because the unit type has only one value, the minimum bound of the unit type is unit, and the max bound of the unit type is also unit. If we want to guide GHC's type system into making a different choice than this default choice of unit, we can do this by providing an explicit type annotation. If we say we want the minimum bound for the int type, we get this, which is the integers are 64-bit integers, signed 64-bit integers, and this is the minimal value representable, and this is the maximum value representable. And actually, if I add 1 to the maximum value representable, I'm getting an overflow, and I'm ending up with a minimum bound again. There is also min bound for booleans, right? So that is false, unsurprisingly now. Maximum bound for booleans is true. For characters, we have the null character as the minimum bound, which is escaped like this, and the maximum bound I don't even know. This is Unicode, so some sort of large representation. So yeah, and there are a couple of other types, but again, the bounded class has a few more instances than the enum class, but it does have a relatively limited amount of instances. It does have instances for tuples. So if both components of a pair, for example, have a minimum bound, then we can also consider the combination of the two minimum values a minimum bound of the pair. So, for example, if I want to know the minimum bound of the pair of booleans and characters, I get this. Okay, so in the next video, I'm going to discuss the show and the read classes to continue our tour of important type classes. The show class we have been seeing quite a number of times already, because it is the class that is implicitly being used by GHCI for printing results back to us, for spitting out results. And the read class is kind of the counterpart, and is a rather interesting class to work with as well. So that can be very useful. We're going to do that next.